Here the series combination of the problem. Here there are the two metal rods. Metal rod 1 is copper and rod 2 is made of steel. One end is maintained at 0 degrees centigrade, other end is maintained at 100 degrees centigrade. So, one is at lower temperature, another end is higher temperature. So, here in the given question, copper rod joined to steel rod, the rods of equal length and equal cross section. So, here L1 of this copper rod and L1 of L2 of the steel rod are same, equal cross sectional area A both are the same. The free end of the copper is kept at 0 degree centigrade and that of steel rod is kept at 100 degrees centigrade. He is asking that the temperature at the junction of these rods. He is given this copper K1 value and steel K2 value. If you observe this, it is maintained at the higher temperature steel rod. The copper rod is maintained at the lower temperature. Definitely the heat flow moves from point of higher temperature to lower temperature. That's what we discussed so far. So, heat flow moves this direction. So, from the steel to the copper. See, look at that. This is the copper, this is the steel. It is maintained some 100 degrees centigrade here. It is maintained 0 degree centigrade. Here, heat flow, it moves like this direction. He is asking the temperature at the junction. This let it maintains a T here. After reaching the steady state, the heat current that should be uniform from this end to this end, again this end to this end. How can you find out that heat current, that is dq by dt is equal to I, this can be equal to Ka dt by dx. So, here first steel rod, we are taking that Ks value, area of the cross section here A here, and dt we are taking 100 minus T, and dx, the lengths, they are both are having same length is given L. This is current flows from steel rod which is maintained at 100 degrees centigrade to temperature T here. This is our assumption, that is our target variable. We have to find out the T value at the junction. Next, if I am writing the same current equation for this copper. So, copper I am taking that Kc value here. This is the coefficient of thermal conductivity of the copper. Area of the cross section for both the things are same. That is what I am taking that same A value here. Here the temperature difference, here it moves from here to here. So, higher temperature is T, lower temperature is 0. That is what we are taking T minus 0 by L. After reaching the steady state, definitely this current and this current both are the same. Hence, we can equate Ks A 100 minus T by L will be equal to Kc A into T minus 0, I am writing T again, L. L gets cancelled, A gets cancelled. So, if we are taking substituting this value of Ks into 100 minus Ks into T is equal to Kc into T. So, Ks into 100 by Kc plus Ks is equal to temperature T here. In the given question, Ks and Kc values are given. Here copper coefficient of thermal conductivity is 390 in the question is given, whereas the steel rod is 46 here. You substitute these corresponding values, you will get that temperature at the junction. So, whenever they are asking the questions based on how to find out the junction temperature, simply in the series combination you can take this, the steady state, the current flow through from metal rod, one metal rod is equal to current flows to the other metal rod. So, always you take the temperature difference. Students, they get confused about this, how they take the temperature difference. Suppose if you are taking this 100 degrees centigrade, this is a 0 degree centigrade, always direction of flows from higher temperature to lower temperature. First you choose this direction first. And steel rod, what are these ends? Let this 100, here there is a junction, so your assumption is T here. So, you take the temperature difference 100 minus T and corresponding length you substitute. What about this copper here? The current heat flows from again this direction. Here it is maintained, it is 0 degree centigrade, other end is maintained at T degree centigrade. T will be more than this 0. So, you can take this T minus 0, that is what you can substitute this. This is about to find out that junction temperature. Here two rods, they have identical geometrical dimensions. So identical geometrical dimension means both have the same length and same area of the cross section. They are in contact with the two heat baths at temperature 100 and 0. So here this end is maintained at the 100 degrees centigrade, this end is maintained at the 0 degrees centigrade. Here the temperature of the junction is 70 degrees centigrade. He is given this junction temperature also 70. But he is asking the temperature of the junction if the rods are interchanged. See here, suppose this is the metal rod 1, this is the metal rod 2. If rod 1 is connected to the 100 degrees centigrade, the junction temperature is 70 is given. He is asking, suppose rod 1 can be interchanged to this rod 2 and rod 2 comes to this position. So what is the junction temperature? It can be maintained. That we are going to discuss now first. First, the given conditions. This is the metal rod 1. This is the metal rod 2. Here metal rod 1 is maintained at 100 degrees centigrade and this one is 0 degrees centigrade. Here that coefficient of thermal conductivity is K1 I am taking. This one is coefficient of thermal conductivity K2. This is my assumptions. And both have same geometrical dimensions. So we can assume this area of the cross section is A and length L here. Here also A and L here. Just now I explained that how the heat current flows always flows from higher temperature to lower temperature. Here it's maintained at 100 degrees centigrade. Here it's maintained at the 0 degrees centigrade. Definitely your heat direction, it moves this way. This is heat flow. First you apply the current equation for this metal rod 1. Let it maintains the junction temperature is already junction temperature is given, that is will be 70 degrees centigrade. If I am writing that current equation, first K1 area of the cross section and dt minus dx. So here 100 minus t by L, this one. And again if I am writing for the same current for the second metal rod K2A, here the 70 minus 0 by L. Here the junction temperature is T value is given. We are taking this one is 70. So given value. If you are equating this both the currents, because at steady state what happens that heat current is same. If you are equating both the cases, so definitely we can write down K1 by L A 100 minus 70 30, that can be equal to K2A, this is 70 by L. So A by L gets cancelled. So you will get the relation of this K1 by K2, this can be equal to 70 by 30, we can write down 7 by 3. Now we got the relation of K1 and K2, but he is asking the same arrangements. So 100 is maintained as it is and 0 is maintained as it is. So previously rod 1 is connected to 100 degrees centigrade. Now rod 2, metal rod 2 is connected to 100 degrees centigrade. Here this is about rod 1. He is asking this T value. So rod 2, what is our assumption? Coefficient of thermal conductivity is K2. Here area of the cross section is A here and length L here. Here the K1, A and L. Obviously heat flows from higher point temperature to lower point temperature, 100 to 0 degrees centigrade. Same here also heat current flows from this same direction. If you are writing the current equation for this second configuration, I is equal, if you observe this, K2 A 100 minus T, T is unknown here, we have to find out, our target variable is T, by L, and here this case K1 A T minus 0 by L. If you are equating both the same, K2 A by L is getting cancelled. Directly I am writing 100 minus T is equal to K1 into T. So already we know this K1 by K2 is equal to 7 by 3. 100 minus T is equal K1 by K2. If it moves to side, K1 by K2, 7 by 3 into T here. So it will be 300 minus 3T, this can be 70. So 10T is equal 300, T is equal 30 degrees centigrade. whereas in the first configuration we are getting the junction temperature is 70 degrees centigrade. Although their combination of the rods, they are maintained at the same temperatures. One is maintained at 100 degrees centigrade, other is maintained at 0 degrees centigrade. Here also same metal rod combination is maintained at 100 and 0, but the interchange, rod 1 is connected to this side, rod 2 connected to this side here. So if you are changing this combination, definitely your I value has to be changed, because initially it's a 70 is maintained, now we got that 30 degrees maintained. So heat flow that depends upon this combination of the metal rod, although they are connected in the same temperature differences. If you go for another model of this question, same model of this here. So semicircular rod is joined at its ends to the straight rod of the same material and same cross-sectional area. So here the two metal rods, one is maintained as a semicircular rod, one more is straight rod. Both are maintained at the same temperature. That means both have same coefficient of thermal conductivity. Both have the same cross-sectional area. He is given this area A is also same. The straight rod forms the diameter of the other rod. The junctions are maintained at the different temperatures. He is asking that find the ratio of heat transferred through the cross section of semicircular rod to the transferred through the cross section of straight rod in a given time. So there are the combination of the two metal rods. One is semicircular like this, is joined at its ends to the straight rod. So again the straight rod, it forms the diameter. That means this is the metal rod 1, this is the metal rod 2. Both have what their assumptions are, both have A same, and also both are maintained at the same material. So coefficient of thermal conductivity K is also the same. And next heat, he is asking the ratio of heat transferred through the area of the cross section of semicircular rod to heat transferred to the cross section of straight rod. He is given the junctions are maintained at the different temperatures. So this is the junction 1, I am calling as A here. This is the junction of 2B here, this is the B. I am taking this temperature T1, T2. He is given that different temperatures. So I am taking this as a T1 and this is a T2. So our assumption solving the questions, T1 is greater than T2. So heat flow can move this direction along the semicircular rod, whereas in the straight rod this way. Suppose if your assumption is T1 is less than T2, your heat flow, it moves along this side from T2 to T1. For the along this metal rod this side. Both the assumption you can do this. So heat flows from, let T1 is greater than T2 now. First heat flows from here to here. So how can you take this heat flow dq by dt? Ka temperature difference. So T1 minus T2 by L. So here let this particular semicircular radius is R here, length of this one is pi r. This is the current due to semicircular rod, whereas I2 value here, it can be same dq by dt. So K is same because both are maintained the same temperature, both maintained the same material, and A is same, area of the cross section is same, and dt is also T1 minus T2 for both the things is same because they are connected to the same junction temperatures. This metal rod is connected with A and B. This semicircular rod is connected to T1 and T2, but this length is different. For here it will be the pi r, it will be the, it forms the diameter in the question directly is given. So here we are taking this 2r. He is asking that the ratio of heat flow, so d1 by I2 he is asking. Simply if you are taking this side, Ka gets cancelled and T1 minus T2 cancel, R cancel. So you can get this 2 is to pi.